All right, let's get started. Already pretty late. I guess everybody's looking for cake and some break now. In the last session today, I want to introduce a slightly different perspective on cloud security. And instead of most of the talks we've seen today are focusing on basically the front door. Attackers finding vulnerabilities in your application, your dependencies, your supply chain, and so forth. With always encrypted Kubernetes, I want to take the angle of the actual infrastructure you're deploying on. Essentially deploying stuff on other people's computers, even though the other people might be a corporate like Google, Amazon, and so forth. But in that environment, there are other tenants, other cloud customers. There's an admin, a data center employee, somebody that has direct access either to the hardware or the software stack that's below what you deploy. And also often considered, there might be some state actors, some very powerful organizations that have access to that infrastructure, to the supply chain of that infrastructure, and might access your application from there. So slightly different angle. And I would summarize them as infrastructure-based threats. And we daily see that these are real. You can see people exploiting stuff in Amazon or Azure, finding vulnerabilities, and then have access to other people's secrets, data, and their deployments. So how can we protect against these powerful types of threat models here? And the solution I will focus on in the next 25 minutes is called confidential computing, or is referred to as confidential computing. Who of you have heard of confidential computing before? Only a few, that's fine. I will go into what that is in that session. So the two exciting new properties is that we now have hardware that allows us to create runtime encrypted environments. I mean, anything I run inside there is encrypted in use while it's running. And at the same time, and this is very important and often forgotten, is that it provides a way of verifying what's running in these environments. So I can have a cryptographic proof from my processor about what code was loaded in that environment is currently running there. And this is exposed by the latest hardware in the form of confidential VMs. That means I can ask my hypervisor to create a virtual machine on that hardware that is isolated from all other machines. That is runtime encrypted. That means the main memory is encrypted. If I go to the data center, I rip out the memory and try to extract any information, it's just garbage, it's encrypted. And they provide means of obtaining an attestation statement, a certificate that's signed by the CPU that has a certificate chain back to the hardware vendor that says these memory pages were loaded, these hashes are running inside there, and I can verify that versus what I expected to be running there. And this is the first iteration of confidential VMs was probably provided by AMD with AMD SCV a while back. Now Intel is coming up with TDX as a successor to SGX. Maybe some people know that. And ARM will be having something soon. Also, there is work groups for RISC-V creating architectures for the RISC-V ecosystem. But that's not important. All important is to understand that we can now have isolated virtual machines. And these are already existent in the latest generation of these processors. So if I go to one of the big cloud providers today, I can boot and start a confidential VM. They all have their confidential offerings, so that's great. I don't need any special things there. It's already available. So the question is, what are the applications? Who wants runtime encryption and attestation? Who wants this confidential computing? And as Mark Brasinovich, the Azure CTO, put it, the early adopters are the paranoid and the highly regulated. Just to give you an example, for example, the e-prescription service, the EPA in Germany, is running with confidential computing. So stuff that has highly sensitive information inside from the financial industry, healthcare, public sector. But what I see and what others see, that somehow we need a kind of let's encrypt movement for this encryption in use, right? Maybe some of you remember the times when it was very hard to get a TLS certificate for their website. So people were saying, wait, I'm just running a blog. I'm not a banking service. Why would I need HTTPS for my blog? But with making this easy, making this accessible, let's encrypt move the whole internet to using TLS and HTTPS today. And similarly, we can say that there could be a movement where we don't even think about using confidential computing. We will just have runtime encryption for all our workloads. It's just there as a baseline. And to get there, we need to make things accessible, usable, similar to how Let's Encrypt made that thing for transport encryption. So how are these things now consumed as a developer or DevOps engineer? How can I make use of confidential computing to protect my workloads and my applications? And I would split that into 3 kinds of levels or tiers. I think the first applications were in the direction of key management and key services. This was just a software replacement for HSMs, for hardware solutions to store keys. The problem is once I consume those keys in my applications, they are again in an unprotected environment. It's a very specific use case. And the next step was then that we have single individual applications. That could be a container or just a process or multiple containers that are individually packaged into such confidential environment. So I run my individual containers inside in such context. And this is great. The problem is it's really hard to consume, right? Now I have to think about all those DevOps tasks. How can I mesh them together? How can I establish secure connections between them? How can I orchestrate them securely? And maybe I need to repackage, rebuild. This doesn't really fit an ease of use for my application development. So now the third level and where we need to get at is making this whole deployment story, the DevOps story around it, sound and usable for people, so you don't have to adapt much to use this new concept of everything is always encrypted and I can verify what's running. So today, if I want to go from level 2 to level 3, I can say I want a Kubernetes cluster where all my nodes are already running in confidential VMs. That means the Kubernetes node, typically a VM, is now a confidential VM. And I can consume that, and AKS can do that, GKE can do that. You can have confidential VM types for those, for your worker nodes. The problem here is, what I get then is runtime encryption for everything that I deploy in those worker nodes. That means the connections in between are not encrypted, the edges when I write to disk, when I write over network. My API server is not trusted. So the only real threat model this protects against is a data center employee ripping out, or a malicious actor ripping out my hardware and trying to extract information from there. More or less, all other scenarios are still very wide open. So where we want to get at is closing those gaps, making the entire cluster verifiable and the things that happen in between my nodes, and making this really, using the remote attestation to really verify that. And this is what Constellation, the Constellation project, is aiming for. And we will see now in the steps how we get from confidential VMs for my nodes to this entire confidential cluster. The first step is exactly what we have with GKE, plus the API server also in confidential VMs. So the interesting part is now how does it work? How can I verify that a node is a confidential node and what is running inside that node? So if I take the node, a usual Kubernetes node as a virtual machine. The first thing that's running there is the firmware. Then I have the bootloader. The bootloader loads a kernel and all the components that come with the kernel, like your init, RD, and the kernel command line, and so forth, that can be all packaged inside a unified kernel image. So these things boot up, and to make this verifiable, we need a concept of a measured boot. That means every component that runs measures the previous component before running it. Measuring just means creating a hash before loading that into memory. And this is exactly what happens in a Constellation node. That means we have an exact fingerprint of such boot, and we can verify that against what's booted by the cloud provider. So we say, hey, boot as a Constellation node. We can verify that exactly this image with exactly that bootloader and that kernel was booted there. On top of that, we then need the file system. And there we follow the approach of an image-based Linux. That means the root file system is read-only. That means I never have incremental changes to my Kubernetes node image. I just swap and replace. I boot a new node with the new image version and shut down the old one. And this means I can have the root file system as read-only, and I can have it integrity protected. So there can't be any changes to that root file system ever. And then on top of that, I boot the actual Kubernetes node components, so that in this case, a bootstrapper that uses kubeadm to start the Kubernetes cluster, and download the Kubernetes components, download the container image that should be running there. And all of this has some state, right? For example, your container images, they need to be stored somewhere, so there's a read and there's an encrypted and integrity protected stateful disk, and all of the stateful data is stored there. This also allows the same image to boot different kinds of Kubernetes versions, so I don't need to have a one-to-one mapping. I have one image version and then different Kubernetes version that can run on top of there. So this just is one confidential Kubernetes node that's entirely verifiable. So once this has booted up, I can obtain an attestation statement from the hardware, and that gives me exactly the measurements for all of these components. And that's pretty cool. That gives me real node verification. So I know whatever the infrastructure is below, whatever is running there, I'm pretty sure I can cryptographically verify that if I deploy a pod in there, the cloud provider hasn't modified the bootloader with a backdoor or anything like that. So now that I have the Kubernetes nodes, the question is a bit, how does all the other operations I usually do with Kubernetes work, like all the DevOps tasks, the day 2 operations. And usually I can split that into two kind of worlds, the manually managed on-prem world, if you will, and the more managed Kubernetes cloud world. And I guess there isn't really a reason people want the left side. It's just you have to do it sometimes, but ideally everything would just work, right? You wouldn't need to do manually steps. So with confidential computing, we want a meeting in the middle approach. We can't have the cloud provider have access to our cluster. That would break the isolation aspect of it. At the same time, we don't want to manually manage everything. So the idea is to automate most of the tasks while having it completely isolated, so making it as autonomous as possible. And concepts to implement that follow the typical operator controller pattern. Most of you might be familiar in the Kubernetes world. So we deploy a bunch of services that take on these tasks. So I can have a descriptive update of what I want to have in my cluster, and then the operator controller takes care of bringing the cluster into the desired state. How this works, for example, if the join service, just to give an example of one of these tasks. So let's say I want to scale my cluster, I want to add a new node. How can this new node join my already verified confidential cluster without me going ahead verifying this node and then adding it? So the join service will do an TLS handshake, but this handshake is not based on some known root certificate, but instead of a attestation statement provided by the hardware. So the new node will obtain an attestation statement, will include its public key as part of the payload data of this attestation statement, and provide it to the joint service of our cluster. And the joint service knows what a good configuration is by its own configuration, and verifies this attestation statement, and only accepts nodes that confirm to that. And then they have a secure channel established on the remote attestation, and then they can join the cluster in a usual kubeADM way. So this brings us to the state of now we have all our nodes running in confidential VMs. We have the API server. We can trust that the entire cluster follows my specification. Everything is verified, and I can obtain an attestation statement that transitively allows me to say all of my nodes here are indeed running the exact image and components I expect them to run. So what's missing here is then the other states of encryption. In the presentation before, we had those three states, right? In transit, at rest, and in use and at runtime. So the other things at rest and in transit are solved problems. We already have that. We already have the encryption in transit. We already have the encryption at rest. So we don't need to reinvent the wheel and just plug in what's already there. So for encryption in transit, we make use of Cilium for several reasons. But one thing is we can actually make sure that all packets at all times will go through the Cilium WireGuard layer. They will never be sent over the network without encryption. This required some changes to the pod-to-pod encryption mode in Cilium. There's some blog posts coming up soon about that. But yeah, that means encryption in transit is done. Encryption at rest is maybe interesting. We've seen in another talk that how all the Kubernetes components work, and that we have the etcd that can be encrypted. Etcd can encrypt the data it writes to disk. Unfortunately, it doesn't have integrity protection out of the box yet. So this is why we store the etcd data on already encrypted storage that is has protection for integrity and the confidentiality. Well, that's also easy, so we can store the etcd state on encrypted disks. You can back up those disks, you can restore those disks. That works. And then, at least if one etcd node is still alive, this will also happen automatically, so no manual interaction. The second thing then is encryption of your actual data volumes. So if you say in Kubernetes, hey, my pod, my container needs some persistent state, has some persistent, wants to consume some volumes, you can define that. You can plug in storage via CSI, via the container storage interface. And most cloud providers already offer to do that with encryption. The problem is we want to keep the cloud provider out of the loop. We want to isolate from the infrastructure. And these encryption technologies, they work by encrypting it in the back end. And this is not verifiable by us. So here we need encryption at the node level, in the context of the confidential VM. So currently the way it works is there are CSI plugins that just plug in encryption to the existing CSI plugins, for example, for Azure Disk or GCP. And then if you don't want block storage, if you want file storage and blob storage, you need to have something in the cluster itself. So you can't consume Azure files, Azure blob, or just as an example. You would need an in-cluster solution, and this is currently done via RUCSEF, a CNCF project, if you're not familiar. So bringing it all together, we now have a fully isolated cluster. That means encryption at rest, encryption in transit, and encryption at runtime. And we can verify this cluster. I mean, we can obtain an attestation statement, and we know that's in a good state. And then we can go ahead and just use Kubernetes as we used to. I actually have a bit of time, so I can show a quick demo. But essentially, the UX for Constellation itself is a CLI that allows you to quickly create a cluster at any of the major cloud providers. You could also do that with Terraform. So you can create if you have infrastructure as code, you can create the infrastructure with Terraform already. You just then need the CLI to do this verification part. This is an upcoming feature that will allow you to also do that with Terraform directly, but currently the verification at least needs to be done via the CLI. Maybe I can pull up the demo. Is that big enough to read? So I can create a configuration. The configuration just says, hey, this should be that Constellation version, that Kubernetes version. It's just a descriptive YAML file that you can then edit and descriptively change the state of your cluster if, for example, use a GitOps pipeline. So I can generate a config for GCP, for example. There's already one. I pre-generated it because I need to insert some information about my cloud subscription, my access to the cloud provider. And then I have a configuration file, and with that configuration file, I create my cluster. I say how many initial control plane nodes I want. I wouldn't use one. One is not production grade, but you can do one if you want to. How many worker nodes, and then you give it a name. And this will provision all the infrastructure. But because this takes a bit of time, I pre-created a cluster that has this step already done. And now we have confidential VMs booted up. They all booted our image, so now it's time to verify using the remote attestation. And therefore, there's the Constellation init command. Init will now do the process I described using the attested TLS, the TLS based on attestation, to establish a connection to the cluster. It will verify the attestation statement and then bootstrap the cluster. And also this takes a bit of time. So I already did that as well, and the output is a bit broken here, but essentially what you get at the end is a kubeconfig file then you can plug into your kubectl and use Kubernetes from there. Right, so this is now a ready cluster, and I can deploy applications like Nginx and scale it, and will support all the features you would expect from a Kubernetes. Yes. Okay, going back to the presentation. So quick summary. Constellation is maybe I should mention that, as an open source project. You can go ahead, you can create isolated clusters at most of the big cloud providers, also OpenStack. You can then just deploy your applications from there and be sure that nobody from the infrastructure can have access to any of your data and your workloads. It doesn't solve all your problems, of course. All of the other things that we heard today are still true. It's just a different angle. It's just protecting from the infrastructure, and then you can protect from the front door and your supply chain and so forth. It changes who you have to trust. It reduces your trusted computing base, it's what's usually called, to just what's running inside your confidential VM context. That's the guest OS and the Kubernetes application layer. As I've shown, you can then verify that and pin it down to the actual source code level of what's running inside. Oops, wrong button. This is a very new topic. It takes some time to, I guess, to wrap the head around. Next week there will be the online conference called OC3, Open Confidential Computing Conference. That's a free conference you can sign up on. If you're interested in this topic, there will be a bunch of talks just about confidential computing and how this can be used also in a cloud-native way. Just as a advertisement here. Yes, so this is the end. You can check it out on GitHub. You can create a cluster using the CLI. There's also documentation for all the concepts I explained a bit more in detail. Yeah, and there's a Discord channel if you're interested. Feel free to join. Thank you. Any questions? Yes.
Oh. That keeps me awake. That's good.
Hi.
Hi.
Thank you for the talk. You said, please clarify if there is a misunderstanding of confidential computing. In runtime is also encrypted.
Yes.
So let's say the application created some temporary file on some temp order and need to access these files sometimes time. So it is that should the application decrypt this data right to consume it again?
Okay, so as long as wherever this temp folder is mounted is inside the main memory, it's always encrypted. The hardware takes care of encrypting that, and it takes care of that you have continuous access to that. Once you mount it to disk, if you don't use the CSI way of transparent encryption, you would need to manually encrypt it still, right?
Is there any metric sense out there how this impact on the application performance?
Right, there are multiple benchmarks on that. I don't have a link for the direct documentation here, but you can, from the GitHub, you find the documentation. There's also a benchmark that links to other benchmarks as well. So there are two types of overhead. There's the overhead of runtime encrypting the main memory, right? And Azure did that, GCP did that. It depends on the workload, it depends on what it does, but it's usually between 1 and 10%. Just runtime overhead for main memory encryption. And then there is some I/O overhead, but it's if you already do transport encryption, if you already do storage encryption, it's more or less the same, right? It's not that much more. I'd say it's highly dependent on the application, but it's between 1 and 10% overhead is what the most benchmarks tell you.
Okay, because I think it depends on the algorithm which will the encryption make it. It might also change this impact.
Yes, so exactly. So if you, for example, with the network encryption with Cilium, right? I think with Cilium we can, if on a 10 gigabyte network, you can get close to 10 gigs. Not exactly, but then we use the WireGuard encryption. You could switch to IPsec, and in certain scenarios it might give you a different performance. But with WireGuard, you have the usual WireGuard overhead, and so forth.
Thank you.
Yeah.
Other questions?
To what extent does it also work on bare metal, or is it out of scope? Or
So it works on bare metal if you have the hardware that has that. Currently, you can't deploy Constellation on bare metal. There's a mode that allows you to do that with KVM QEMO or with OpenStack, but just when we talk about real bare metal, it's just not ready for that yet.
Is there a way to transition an existing cluster into a Constellation mode by swapping node by node, or do you have to create a new cluster?
Unfortunately, you have to create a new cluster. Yeah.
Okay, thank you.
More questions? If not, then many thanks to Moritz, to all the speakers for today.